Great to see you here. Welcome again to one of the new videos of the Ceuster Academy. My name is Luc de Ceuster. I'm the founder of the Ceuster Academy, and here we're going to look at some modular exponentiation and how to resolve these. But before we start, click on the subscribe button, click on the bell button, so every time we have a new video, you will be informed by YouTube about it. So let's have a look at modular exponentiation. Now we try to calculate the 273rd power of 7 modulus 45. Now we can calculate those powers, but when you see that those powers are very high, those numbers become very large. And that gives problems to the computer because we get a data overflow. Now, the modular exponentiation method is very interesting to resolve these problems. Now, before we start, I want to remind you two very important rules about powers. Remember that x to the power a to the power b is equal to x times ab. So when we take a power of a power, we multiply the powers. The same thing here when we have the same base, x to the power a times x to the power b is x to the sum of a plus b. So we use those rules. Now what are we going to do here? First we start with the exponents, and we take the first one, which is 7 to the power 1 modulus 45. Well, this is very simple because 7 modulus 45 is 7. Now we are going to double those coefficients, and we will see that they grow exponentially. So we have 7 to the square modulus 45, which is 49 modulus 45, is in fact 4. Now what we have is we go to 7 to the 4th modulus 45. We still can calculate that, but it's basically the same as 4 to the square modulus 45, which is in fact 16. We do the same again. We have 7 to the power 8 modulus 45, and we take 16 to the square modulus 45. So 16 to the square is 256 modulus 45, and that is equal to 31. We go to 7 to the power 16 modulus 45. We take 31 to the square modulus 45, and when we look at 31 to the square modulus 45, when you do the calculation you will find that this is 16 again. And now 7 to the power 32 modulus 45 is 16 to the power modulus 45, and we have the same like here, which is 31. And what do we see? We have a repetition. We have 16, 31, 16, 31. So 7 to the power 64 modulus 45 is in fact 31 to the square modulus 45, which is 16. 7 to the power 128 modulus 45 is like 16 to the square, and we find 31. And 7 to the power 256 modulus 45 is again 16. Now we're going to use the rule of the powers, and we can say that 273 is equal to 256 plus what we add now is 16 plus 1. So what we're going to do now, based on this, is we're going to calculate 7 to the power 256 times 7 to the power 16 times 7 to the power 1 modulus 45. 7 to the power of 56, we know this is 16. All in modular mathematics, of course. 7 to the 16 is also 16. So basically what we have here is 16 to the square times 7 modulus 45. 16 to the square, where we have it, 16 to the square is 31. So we can say that this is equal to 31 times 7 modulus 45. And 31 times 7 is in fact 217 modulus 45, which gives us 37. Now we can use this calculation, which is very interesting when we have very large numbers here. But in this case, and I will do it in green, we can also say that basically this is 16 to the square times 7, 16 to the square times 7, and I have to find the number on the board. Where do I have it? And I found a number. This is 1792 modulus 45, which is also equal to 37. So basically what we found here, and sorry for the interruption, I was looking for this number. I don't have the calculator here with me. This is still acceptable, 16 to the square times 7, 1792. But imagine that we have very large numbers here. Then the method that we used here is more interesting, because we can say that 16 to the square modulus 45 is in fact 31. We multiply with 7 modulus 45, and when we calculate that, we find that it's equal to 37. Let's do another exercise so that you get used to this way of calculating, this way of doing the modular exponentiation. The second exercise is 15 to the power 427 modulus 33. We want to find that number. So like in the previous one, we started with 15 modulus 33. That's easy, it's 15. Then we have 15 to the square modulus 33 is 225 modulus 33, which is equal to 27. Now you can do the calculations easily. 15 to the power 4 modulus 33 is 27 to the square modulus 33, and 27 to the square modulus 33 is 3. Then we have 15 to the 8 modulus 33 is 3 to the square modulus 33 is 9. Then we have 15 to the 16 power modulus 33 is 9 to the square modulus 33, and 9 to the square modulus 33 is equal to 15 again. Then we have 15 to the power 32 modulus 33 is 15 to the square modulus 15, and I can go back here, which is 27. Then I have 15 to the power 64 modulus 33 is 27 to the power 2 modulus 33 is 3. 15 to the power 128 modulus 33 is the square of this, 3 to the square, so that's 9. And 15 to the power 256 modulus 33, 9 to the square is 15 again. So what we see here is that we have a repetition here. From here we repeat again. So 15 to the power 512 modulus 33 will be again 27. So that's the repetition that we have. Now when we are going to look at the number here, the 427. So when we look at the 427, 15 to the power 427, 427 is in fact 15 to the power 256 times 15 to the power 128 times 15 to the power 32 times 15 to the power 8 and then 15 to the square times 15. And now we're going to look here in the list. So we find 15 to the power 256 modulus 33. So that gives us 15. Then I have 15 to the power 128 modulus 33. This is equal to 9. Then I have 15 to the power 32 modulus 33 is 27. 15 to the power 8 is again 9. Then I have 15 to the square is again 27. And 15 itself is 15. Now I can look here at the numbers and I can combine them, so I can say 15 to the square modulus 33. 15 to the square, that's 27. Then I have this one and this one, then I have 27 and 27. 27 to the square modulus 33 is, where do we find 27? That's equal to 3. And then I have 9 to the square. 9 to the square is again 9 to the square modulus 33. We find 9 to the square is 15. So basically what we find at the end is that we can replace 15 to the power 427 by 27 times 3 times 15 modulus 33, which is, when we multiply this, it's 1215 modulus 33, and this gives us finally the result that this is equal to 27. So based on all these calculations, these different steps are in fact very easy to follow. We have calculations with low numbers, not all those high numbers, not 15 to the power 427, and we see that the result of 15 to the power 427 modulus 33 is equal to 27. Now this is a very interesting method, but there is also the fast method, and we're going to look at a faster algorithm to do these calculations. It's a little bit different, but you will see that the fast exponentiation algorithm will provide a very fast way to do these calculations, and we can easily program it in our computers to do these calculations. Another way to calculate that modular exponentiation is using the fast exponential modulation algorithm, also referred to FEMA. This is the example we're going to look at, 14 to the power 9 modulus 28. And we can say that this is equal to m to the power a modulus n. M in this case is equal to 14, e is 9, and n is 28. What we're going to do is in different steps. Step 1, we're going to write e 9 in base 10 as a binary number, and it's 1001. Step 2, we're going to calculate, depending on those parameters, we're going to say when a, the coefficient is 0, we have only d squared that we calculate, and we calculate the modulus of it. When the coefficient is equal to 1, then we have d square n dm, and we start with d initial, d0 is equal to 1. So let's have a look how this works, and I will do it in blue. So we will see this. First of all, we say d is equal to 1. The first number here is 1. So we are going to calculate the square and multiply d, the new d, with n. So 1 to the square is 1. We multiply d with n. So we have 1 times 14, so 14. And 14 modulus 28 is equal to 14. The next step, we have the 0 here. We use the 14 to the square, which is in this case equal to 196 modulus 28. And when we calculate this, this is 0. Now, that's in fact very interesting in this case, because now we have 0, so d is again 0, and the last one 0 to the square, and 0 times 14 is also equal to 0. So basically what we find here is 14 to the power 9 modulus 28 is equal to 0. And that's the end result. Now we can do this with different numbers, but we always do the same step. So when the coefficient of the binary number is 1, we take the square and we multiply with the m, with the coefficient here. And of course we always reduce it to the modulus, in this case 28. But let's do that with a more complex example. Let's have a look at this more interesting example. Now I take 13 to the power of 5 modulus 27. It is clear you can calculate this without any problems. We don't have to use this procedure, but it's very nice to show the procedure with this application. E is 5 base 10, so we write it as a binary number, which is 101. M is 13 and n is 27. So basically we start with d equal to 1. We have the first one here, so we have d square is 1 to the square, of course, is 1. Since this is equal to 1, now I have to calculate m times d. M times d is in fact now 13, so we have 13, and we look at the modulus, 13 modulus 27, and we know this is 13, so that's basically very quickly calculated. Now we have 0. Now this is the new d, so d to the square is 13 to the square is 169. When we look at this, now we have to calculate 169 modulus 27, and that number is equal to 7. And the last element here that we have to do, the one here. So now we have the new d, which is 7 to the square now, is 49. So we have 49 modulus of 27, which is equal to, when we take 27 minus, and we subtract it from 49, we see that this is equal to 22. Since the coefficient is equal to 1, so I have to multiply with 13, so I have md is 22 times 13, which is equal to 286. And we calculate the modulus again. 286 modulus 27 is in fact equal to 16. And this is the final result. So basically we can say that 13 to the 5th power modulus 27 is equal to 16. And you see this is a very fast algorithm. We only have to write the coefficient, the power, as a binary number and repeat this procedure till we reach the end of the binary number. And we can program that quite easily. and use this in further calculations. So that's what I wanted to talk to you about modular exponentiation. It's a technique that we're going to use in many more applications. We will use it later, for example, in encryption and decryption. These are the things that are very typical applications of this technique. Yes, we're at the end of the video. Don't forget to subscribe. Click the subscribe button, click the bell button, and every time we have a new video for you, you will be informed by YouTube. Thank you very much and see you later. Bye bye.